Now let's take a look at question number 2 in the study guide, the Chem 110 lab manual, the study guide for the Titrimetric analysis experiment. And this question deals with the second experiment on titrimetric analysis. Now if you're a Chem 154 student, it's very likely that the question will be either the same or very similar, and you should check your Chem 154 lab manual. Now what's happening here is we accurately weigh a sample of a primary standard acid, potassium hydrogen phthalate, and it's transferred quantitatively into an Erlenmeyer flask along with water and dissolved in that water. The primary standard acid solution is then titrated with the approximately 1 mole per litre sodium hydroxide solution to the endpoint. And what the question is asking is how many milliliters of approximately 1 molar sodium hydroxide would be needed to neutralize this mass of the primary standard acid. In other words, what is the titer or the titer figure expected to be? You see, what we're doing here is we're actually standardizing the sodium hydroxide. We want to determine the precise molarity of the sodium hydroxide solution to maybe 4 or even 5 decimal places of precision. And it can be very useful for us to determine the approximate titer figure, because as we approach the end point in the titration, we have to be adding the sodium hydroxide very slowly, in fact dropwise, to make absolutely sure that we do not overshoot the end point. If we overshoot the end point, we're unable to determine the precise titer figure, and for all practical purposes, we would have to start the titration again. So it's very useful to determine approximately where the titer figure is going to be, so that when we approach that added volume of sodium hydroxide in this case, then we add it very carefully, very slowly, drop by drop, until we reach the exact endpoint. So the solution given in the appendix in your lab manual uses the dimensional analysis type approach, so we'll do the same. Always begin, of course, by writing out the balanced equation for the reaction. So here we have potassium hydrogen phthalate. Structure looks like this. We have this benzene ring structure, and here we have a COOK group, and here we have a carboxylate group, a COOH group. So that is what potassium hydrogen phthalate looks like, and it's explained a little bit more in your lab manual what this structure is all about. And it's abbreviated to KHP, meaning potassium hydrogen phthalate. So there's a potassium hydrogen phthalate plus the sodium hydroxide, and that's going to produce the salt. So in this case, in potassium hydrogen phthalate, there is only one acidic hydrogen, one hydrogen that can be titrated or can be removed by a base and replaced, of course, by the sodium. So we get the sodium salt of potassium hydrogen phthalate and water. So this equation is in fact balanced. The stoichiometry is 1:1. So for every 1 mole of potassium hydrogen phthalate that we have in the Erlenmeyer flask, we need 1 mole of sodium hydroxide to completely neutralize it. So if we take a look at the route that we need to take to solve this problem using a dimensional analysis type of approach, we will need to calculate the moles of potassium hydrogen phthalate, and then from there we can determine the number of moles of sodium hydroxide needed to neutralize that. And we do that through the known stoichiometry of the reaction. And once we know the moles of sodium hydroxide, we can convert that to the volume of sodium hydroxide. So we'll begin by calculating the moles of potassium hydrogen phthalate. So we know the mass is 5.8541 grams, that's of potassium hydrogen phthalate, and if we multiply that by this ratio, 1 mole of potassium hydrogen phthalate divided by 204.22 grams of potassium hydrogen phthalate. the molar mass of potassium hydrogen phthalate is 204.22 grams per mole. So if we multiply by the reciprocal of the molar mass to get the grams of potassium hydrogen phthalate to cancel, leaving us with moles of potassium hydrogen phthalate. And then we'll convert that through the stoichiometry to the moles of sodium hydroxide that's needed. So if we multiply by 1 mole of sodium hydroxide per 1 mole of potassium hydrogen phthalate, that's the stoichiometric ratio. We do that, we get the moles of potassium hydrogen phthalate to cancel, leaving us with moles of sodium hydroxide. So now we can convert this to volume of sodium hydroxide by multiplying by 1 litre of sodium hydroxide per 1 mole of sodium hydroxide. The molarity is approximately 1 mole per litre. So we multiply by the reciprocal of that, because by doing that we get the moles of sodium hydroxide to cancel, leaving us with the volume of sodium hydroxide in litres. And it remains for us to convert that to millilitres, because we are asked to report the volume in millilitres. So we'll multiply by this conversion factor here, 1000 millilitres per litre. Doing that, we get the litres to cancel out, leaving us with units of millilitres. So if we perform the calculation with a calculator, we will get a result. Our calculator will show this value here, 28.665554 millilitres, and we have to report this to the nearest 1 millilitre, so we're going to round that up to 29 millilitres. So when doing this titration using this mass of potassium hydrogen phthalate, we would expect to reach the end point after adding approximately 29 millilitres of sodium hydroxide.